Welcome to this performance on vapor compression test strip. Okay. Now the aim of this experiment is to calculate the actual COP, theoretical COP and Carnot COP of the refrigeration process. Right. As you can see the experimental setup, there are four important components. Here is the compressor. After compressor, your high pressure, high temperature vapor refrigerant will go to the condenser where heat will be rejected and your high pressure, low temperature liquid refrigerant through the rotameter from where the mass flow rate of refrigerant will be measured through the filter and dryer. Why filter and dryer is important? Because there should not be any moisture present in it. If moisture is present, that will become ice and that may choke the capillary tube. After that, here we have used two expansion devices. One is the capillary tube and one is the thermostatic expansion valve. Okay, so this thermostatic expansion valve is operated, the valve, this is solenoid operated valve, right? And this is manually open valve for the capillary tube. We will keep both the valves open, right? So after switching on, there is a SOP, standard operating procedure, that we have to follow. So the first that we need to switch on the solenoid switch. If that sound will come, means it has switched on, right? Then next switch on the condenser fan. Okay. Then switch on the compressor switch, right? Here high pressure, low pressure cutout is also there. That is a safety device, control device. If pressure will go beyond certain limit on higher level as well as on the lower level, then it will switch off the compressor, right? So here we will record the 5 temperatures, right? Which are those 4 temperatures of refrigerant at 4 positions, right? Temperature before compression is nothing but temperature after evaporation. Temperature after compression is nothing but temperature before condensation. Temperature after condenser is nothing but temperature before expansion. Temperature after expansion is nothing but temperature before evaporation, right? So these 4 temperatures of refrigerant at 4 locations we will record, and fifth one is the temperature of water. This is the evaporator. As you can see, this is the evaporator. Evaporator coil is there, and inside this water is there, right? Heat from the water will be absorbed. Now to measure the refrigerating effect, we have provided heater inside this, right? The amount of heat energy released by the heater, same amount of heat will be absorbed by the refrigerant. So energy released by the heater is nothing but refrigerating effect that we are going to measure, right? So here, as compressor is switched on, you can see that the energy meter blinks has started, right? Now we will measure temperature at each point. You can take the notebook, right? We will create an observation table and we will measure the temperature after every 5 to 7 minutes till the steady state will come. What is the steady state? Temperature is not changing with respect to time. That state is nothing but steady state. So we will wait for the steady state. Once the steady state will come, we will record all the temperatures, higher pressure, lower pressure, the compressor energy meter and heater energy meter, right? So now we have not switched on the heater. Okay. So this is nothing but right now water temperature. This is water temperature. This is after expansion temperature. This is condenser temperature. This is after compressor highest temperature, and this is nothing but your evaporator temperature, right? So we will wait for the water temperature to reach around 5 to 7 degrees centigrade, and then we will switch on the heater. After switching on the heater, this is dimmer stat adjusted with the help of resistor, right? So by trial and error method, we will maintain the temperature of 7 degrees centigrade. which temperature we will maintain? Temperature of water by trial and error. In case water temperature will rise, we will reduce the heater energy. If water temperature will decrease, we will increase the heater energy. By trial and error, we will maintain the temperature of water at 7 degrees centigrade, above 0 degrees centigrade, because at 0 degrees centigrade it will become ice. So either on 5 degrees centigrade or 7, whichever is, we maintain that, right? Once we will maintain that, again we will wait for 5 to 10 minutes for the steady state to come, right? Then after that, heater will be switched off, right? So we will measure the blinks of compressor energy meter and heater energy meter. From that, power consumed by heater, and heater energy is directly giving you what it is giving you. Directly it is giving you the refrigerating effect produced. Because how much is refrigerating effect produced, that much heat energy is released by the heater, right? So actual COP directly we will calculate by compressor, heater energy divided by compressor, right? Now how to measure the heater and compressor energy? That is very, very important. Now you can see these blinks. What this blinks indicates? The frequency of blinks indicates the rate of energy consumption, right? Now the faster is the blinks, the more is the rate of consumption. Now this energy meter has the energy meter constant of 3200. What does it mean? If this light will blink 3200 times, 1 unit of electricity is consumed. Right? 1 unit of electricity means 1 kilowatt hour. That unit of electricity, a commercial unit of electricity that we use. Okay. So do we need to measure all 3200 blinks? No, we can't measure that, right? So we will measure the 10 blinks or 10 pulses, or we may also call it 10 cycles. How much time it will take for 10 cycles? From that we will calculate the compressor power. Similarly for heater energy meter also, how much time it will take for 10 blinks or 10 pulses or 10 cycles. From that we will use the formula power of compressor, number of pulses or number of blinks in 10 seconds multiplied by 3600 divided by 10. Why 10? Because in 10 seconds. And in denominator 10 multiplied by energy meter constant. A simple formula. From that we will calculate compressor power and heater energy power. Right? That is how we will record. We will take all the readings. After steady state, we will record these blinks, temperature at 5 locations, 4 refrigerant and 1 water, and also we will record the high pressure and low pressure. Currently, we are recording pressure in PSI, right? So currently the higher pressure side is 150 PSI, as you can see, and the lower pressure side is around 32 PSI. As steady state will approach, there will not be much change in the pressure. In fact, pressure will reduce slightly and temperature will change, right? We will not get absolute steady state, but when the approximate steady state will come, means rate of change will decrease or it is negligible, then we will consider that as a steady state. So it will take around 30 to 40 minutes for the steady state to come. Once the steady state will come, we will take all the readings and we will use all those readings for the calculation, and we will calculate actual COP, theoretical COP and Carnot COP, right? So after calculation, we will observe that actual COP will be lower, then second lower will be theoretical, and highest COP will be Carnot. And the value of Carnot COP is limited to 5.74. That is the ideal cycle for refrigeration, which is reverse Carnot cycle. So COP will be maximum of 5.74. No COP will be larger than this, right? This is about vapor compression testing performance. Okay, this is very important for the subject of HVACR, right? As we have taken the readings on the test strip, the readings in the observations table after steady state. Temperature after compressor is 50, which is highest. Temperature after condensation is 30. Temperature after expansion is 2 degrees centigrade. All these temperatures are in degree centigrade. Okay. So temperature after expansion is 9 and water temperature is 10. and the lower pressure is 22 psi, which is equal to 1.51 bar, and higher pressure is 140 psi, which is equal to 9.65 bar. After steady state, this is the reading that we got. Okay, now you can see here, as we have discussed, process 1 to 2 is the compression, right? After compression, there is a condensation. Heat will be rejected at constant pressure in the condenser. Then it will go to the receiver. In receiver, the purpose of the receiver is to supply the uninterrupted continuous liquid to the expansion wall. Right? In expansion wall, expansion will happen. Again, that high pressure, low temperature liquid will convert into low pressure, low temperature liquid. That will go to the evaporator and it will absorb the heat from the evaporator, and refrigerant will convert into the vapor state, and then it will go to the accumulator. In accumulator, the purpose of the accumulator is that it will accumulate the vapor refrigerant and it will separate out the liquid particles, so that into the compressor only pure vapor will go from the accumulator. Right? If there are liquid particles, that will accumulate at the bottom. Only pure vapor will go to the compressor and cycle repeats. Right? Now here our first aim is to calculate the actual COP. COP actual. How to calculate the COP actual? Refrigerating effect divided by compressor power of the compressor. Right? Now refrigerating effect is nothing but heat energy supplied by the heater power. As we have used as a load, we have used heater here, right? So we have the blinks. So how to calculate power in kilowatt with the help of blinks? So number of pulses in 10 seconds in 10 seconds multiply by 3600, because 1 unit is nothing but 1 kilowatt hour. So in 1 hour 3600 seconds are there, divided by how many time we have taken the seconds, time, how much, that is 10 seconds, that is nothing but 10, multiply by here, or you can write time in second, and energy meter constant. Now for heater, what is the number of pulses in 10 seconds? For heater it is 53600 divided by time 10 seconds multiply by energy meter constant 3200. From this we will get the refrigerating effect in kilowatt. Similarly, power required for the compressor is nothing but number of same formula, number of pulses in 10 seconds multiply by 3600 divided by 10 multiply by 3200. Right? If you will put all these values here, number of pulses in 10 seconds, we are getting 4 multiplied by 3600 divided by 10 multiplied by 3200. So here the refrigerating effect actually and the power for the compressor. Right? So in kilowatt, how much it is? Here refrigerating effect 0.562 and power for compressor 0.45. So COP actual we will get 0.562 divided by 0.45. So COP actual is equal to 1.24. This is the first thing that we got here. Okay? Yes. Now, how to calculate theoretical COP? This is the pH diagram for refrigerant R143A. R134A. Right? Now this is the dome. Okay. This is the saturated liquid line up to the critical point. From critical point, this is the saturated vapor line. In between region is the wet region. Region to the left of saturated liquid line is the subcooled region. Region to the right of saturated vapor line is the superheated region. Right? Now these dotted lines are nothing but the constant temperature lines. Now how to locate four points of VCR cycle on pH diagram. For this, first we will draw the lower pressure line like this and higher pressure line like this. Okay. So point number 1 is on the lower pressure line at a temperature of, how much temperature before compression? It is 9. So this is the line of 9 degrees centigrade. So at this point number 1 will come, right? Similarly, there are isentropic lines. So along the isentropic lines, draw the line till it intersects the higher pressure point. So that is our point number 2. Point number 3 is on the higher pressure line at a temperature of 30 degrees centigrade. So this is 30 degrees centigrade temperature line. So your point number 3 will come here. 3 to 4 is the isenthalpic process. So constant enthalpy. This line will be like this. So that is your point number 4. Okay. So 1 to 2 is here compression. 2 to 3 condensation. 3 to 4 expansion. And 4 to 1 evaporation. Right? So from this we will project these points. So here H3 is equal to H4. From the graph we will get how much it is? 242 kilojoule per kg. Similarly we will get H1 and H2. H1 we will get 408 and H2 454 kilojoule per kg. Now to calculate the theoretical COP, look at this. To calculate the theoretical COP, how to calculate theoretical COP? For theoretical COP is equal to refrigerating effect divided by work done by the compressor. Now look at this refrigerating effect happen in the evaporation, which is H1 minus H4. H1 minus H4, and compressor work is H2 minus H1. So from this, H1 is 408 minus H4 is 242 divided by H2 is 454 minus H2 is 408. From this, COP theoretical is equal to 3.61. Right? Now last one is the Carnot COP. So Carnot COP, how to calculate COP Carnot is nothing but lowest temperature divided by highest temperature minus lowest temperature. Now in the system, lowest temperature is after expansion, which is 2 degrees centigrade. Convert this into Kelvin, 2 plus 273 divided by, as there is a difference, you need to convert it to Kelvin. So highest temperature is 50 minus lowest is the 2. So from this, COP Carnot will come, which is equal to, how much it is? 275 divided by 49. 5.72, and this value has to be less than 5.74. So from this we can say that, what we can say from this, highest COP value is Carnot, second highest theoretical, and lowest is the actual, right? So from this we can write that COP Carnot is higher than COP theoretical, second highest, and COP actual lowest, right? This is our experiment. Our aim was to calculate actual, theoretical, and Carnot COP, and we have calculated this. Okay.